So welcome everybody. So it's really a pleasure for me to introduce the next speaker of the Seminario Matematico-Fisico di Milano. And so I just wrote a few words concerning the speaker, but I think he's well known among our community, but I think it's worth enough. So he got Andrea Mondino. He got his PhD in 2011 at SISSA under the supervisor of Andrea Marchiodi, and then he started his research career as a postdoc at Scuola Normale, ETH, and Zurich University, and then he got his first position, let's say, as assistant professor at Warwick, and then he moved to Oxford as associate in 2019. And so in 2022, he became a full professor at Oxford. And so as we know, so he's a well-known mathematician, and he received a lot of prizes, such as Yapikino Prize, the Bartolozzi Prize, and the prestigious Whitehead Prize in 2020. And also he won an ERC starting grant, which is finishing, I think, this year. I'm too soon. And okay, his research interests are in geometric analysis, let's say, and mainly in the realm of differentiable and metric spaces, with particular attention to spaces or words with Ricci lower curvature bands. And and this is the topic of this talk, I would say. So it's really a pleasure to have you here. So please.
Thank you, Giovanni, for a very introduction and for the invitation. I want to express my appreciation to Giovanni and all the organizers of this seminar. So it's a pleasure to be here and to see many friends and the audience. And all right, so today I would like to talk about smooth and non-smooth aspects of Ricci curvature lower bounds. So let me start with something that we all know very well from bachelor degree, which is the Gaussian curvature of a two-dimensional surface. Okay, so let's start with a two-dimensional Riemannian surface. So sigma is a two-dimensional manifold, G is a Riemannian metric. We have the Levi-Civita connection, which tells us how to differentiate a vector field in the direction of another vector field. And we fix a point P in the surface and the coordinate basis, say Ex, Ey, of the tangent space at P. And then we can define the Gaussian curvature in this way. So we take the first vector, we differentiate in the direction of itself and of the other vector, and then we switch the order of differentiation. And we take the scalar product with the second vector, and then we normalize with the determinant. So we can see the Gaussian curvature is basically as an abstraction to the commutation of derivative of vector fields. Right? So that's the definition. If you are more familiar maybe of surfaces in R3, maybe what we studied in second year of university, one can see that if the surface is geometrically immersed in R3, then the Gaussian curvature is nothing but the product of the principal curvatures, and that's the famous theorema egregium of Gauss, which is egregium because the principal curvatures are something which see how the surface is immersed in R3, while from this formula, it is clear that the Gaussian curvature is something which depends only on the metric, so it's something which is intrinsic of the surface. Okay, and then it can also be written as the Jacobian of the Gauss map. Right, so just to fix some ideas, so the model spaces, so for zero curvature, the model space is R2. Indeed, in R2, we can commute the derivatives of smooth vector field as much as we want, and nothing changes, so the curvature is equal to 0. Then the model space in positive curvature is the round sphere. So, and the idea is that the bigger the radius of the sphere, the smaller is the curvature. So a sphere of radius r is Gaussian curvature equal to 1 over r squared. And the model space for negative curvature is the hyperbolic space. Okay, this is curvature in dimension 2. Now, what about curvature in higher dimension? How can we use the Gaussian curvature to define curvature in higher dimension? Okay, let's do it. So let's consider a smooth, curved n-dimensional space. This is a Riemannian manifold. So it's an n-dimensional manifold endowed with a Riemannian metric G, say of dimension at least 3. Okay, now fix a point P in the manifold and take a two-dimensional subspace of the tangent space. Okay, and say this call this space this two-dimensional plane pi, and it's the span of E1 and E2. Okay, now you have this plane pi, and now shoot the geodesics which are tangent to this plane. Okay, for just a very short time. So you have this point P, you have this two-dimensional plane, shoot the geodesics in all the direction tangent to pi, and you see that for very small time, so you get a small two-dimensional surface. Okay. Now you have a two-dimensional surface. You can endow it with the metric G of the ambient space, and then you can compute the Gaussian curvature of this surface using the formula before. And with that, we can define the sectional curvature of the n-dimensional space in the direction of these two vectors, E1 and E2, as, by definition, the Gaussian curvature of this surface at this point. Okay, so basically, just knowing the Gaussian curvature allows you to define the sectional curvature. Okay? And now, once we have the sectional curvature, we can define the Ricci curvature. So basically, the Ricci curvature is a trace of the curvature. So let's define the Ricci curvature in the direction of a vector v, which is non-zero. Okay, so let's start with the three-dimensional case. So we have a three-dimensional space. I want to tell you what is the Ricci curvature in the direction of a vector v. So what you do is v is non-null. So first you normalize it to make it length 1. Then complete it to an orthonormal basis. So let's say E1, E2, and v normalized is an orthonormal basis of the tangent space. And now compute the sectional curvature of VE1, and then do plus territorial of VE2, okay? And then multiply this by the length of V squared. This is, by definition, the Ricci curvature in the direction of V, okay? And if you are instead of in dimension n, you do the same. You complete V into an orthonormal basis, and then you sum up the sectional curvature of V1, V2, V3, Vn minus 1, and multiply it by the norm of V squared. Okay, and if V is 0, you say by definition Ricci is equal to 0. Okay. Now, some notation about the curvature bound. So I'm going to be interested in bounds on the curvature. So what do I mean when I say I have a bound on the curvature? So bound on the sectional curvature is kind of easy. So we say that given a constant k, we say that the sectional curvature is bounded below by the constant k if for every point and every two-dimensional plane inside the tangent plane tangent space at the point, it told that the sectional curvature is bounded by k. So you say that the sectional curvature is bounded below by k if the sectional curvature at every point and every plane is bounded below by k, and the same for upper bounds. What about the Ricci curvature? Now, Ricci, it turns out, it is easy to check that with this definition is a quadratic form. Okay? So what does it mean that a quadratic form is bigger than a constant, which is a real thing? It is by definition, you say that the quadratic form, that the tensor Ricci is bounded below by a constant, a real constant k, if the quadratic form that you obtain by taking a Ricci curvature minus the constant k times the metric tensor G is non-negative definite at every point P. So basically, you are saying that at every point, all the eigenvalues of the Ricci with respect to the metric are bounded below by k. Right, again, now some examples. The model space of curvature 0 is the n-dimensional Euclidean space, which is sectional 0 and Ricci 0. The model space in positive curvature is the round sphere with sectional curvature equal to 1. And then Ricci, remember that we have to trace n-1 direction, so it's going to be n-1. And the model space for negative curvature is the hyperbolic space, which has sectional -1 and Ricci equal to -n-1. Okay. Now, a beautiful branch of modern geometric analysis is called the comparison geometry, and which roughly amounts to answer the following question, very vague question. So we are given a smooth Riemannian manifold, and assume that you have some upper or lower bounds on the sectional or on the Ricci curvature, or you have some curvature condition. What can you say on the analysis, the geometry, or the topology of your manifold? Just knowing something on the curvature. Okay? So what is well known, it is very classical, is that upper and lower bounds on the sectional curvature are a very strong assumption with very strong implications. Let me just mention two landmark theorems. The first one is the Cartan-Adamar theorem, which tells you, which is a very strong topological restrictions on manifold which allow metrics with negative sectional curvature. It tells you that if you have a manifold, and if you know that it carries a metric of non-positive sectional curvature, then the universal cover is diffeomorphic to Rn. So this is very strong topologically because it says that all the topology of the manifold is encoded in the fundamental group. So it's enough to know the fundamental group to know completely the topology of your manifold. For instance, it rules out the possibility of putting metrics of negative sectional curvature on any sphere, any Sn for n bigger than 2. And it implies that all the homotopy groups are trivial from 2 on. So it's very strong topological restriction. Then another very fundamental theorem for sectional curvature is the Toponogov triangle comparison theorem, which basically tells you that which is the characterization of curvature bounds in terms of comparison triangles. So it says that very roughly that your manifold has non-negative sectional curvature if and only if the triangles in your space are more fat than the one in the picture. You are in positive sectional curvature, but if and only if the basic triangles vanish. Okay, and this how you say it in mathematical terms is you write down this is in R2, you go in R2, and you take a triangle having the same distances. So this is equal to this is equal to this, and the length of this is equal to the length of this. And then you have positive sectional curvature if and only if this length here is larger than this length here. Okay, so you are more. And this is not very precise, but what I want to stress is that this condition is purely metric. You just need to have geodesics and distance. Okay, so the Toponogov triangle comparison is a characterization of sectional curvature only in terms of distance of quantities which are related to the distance of a Riemannian manifold. Okay. But this will turns up. It will be useful in a few minutes. Okay. So this is about the upper and lower bound on the sectional curvature. Now, what about the Ricci curvature? Okay, so we have seen that an upper bound on the sectional curvature, say non-positive sectional curvature, is a very strong restriction on the topology of the manifold. Now, what about an upper bound on the Ricci curvature? Actually, it turns out that an upper bound on the Ricci curvature is a very weak assumption and is too weak to get any topological conclusion. For instance, there's a famous theorem by Locamp in any dimension which generalizes a previous result of Gao, Yao, and Brooks in dimension 3, which says that if you take any compact closed manifold, then it carries a metric with negative Ricci curvature. And even more strongly, give me your favorite negative number, minus 1 million, then your manifold would carry a Ricci curvature, a metric with Ricci curvature less than 1 million. Okay, so this is saying that there is no hope to get any topological restriction. Any manifold will carry this metric. Of course, you need the dimension at least 3, otherwise you go in the sectional curvature realm. Okay, so this is about upper bounds. What about lower bounds on the Ricci curvature? Actually, lower bounds on the Ricci curvature gives instead the natural framework for studying comparison geometry. For instance, there are thousands of results. Let me just mention a few. So a landmark result is the Bishop-Gromov volume comparison, which tells you that knowing that the Ricci is non-negative, then the volume of metric balls in your manifold is always less or equal than volume of metric balls of the same radius in the Euclidean space. Okay, and this is just for stability. I mentioned it in Ricci on negative, but you can mention it for any lower bound, and then you have to compare it with the model space that I was mentioning before. So K positive you compare with the sphere, K negative you compare with the hyperbolic space. Okay, so you have a growth on the volume of metric balls. Then, if you're interested more in analysis, for instance, on the spectrum of the Laplacian, if you know that your manifold has a Ricci bounded below by n-1, which is the Ricci of the round sphere of radius 1, then you can lower bound the first eigenvalue of the Laplacian of your manifold with the first eigenvalue on the sphere, and this is the Cheng, this is the Lichner-Orbith spectral gap. And you have plenty of other results. For example, you can control the Laplacian of distance function from a point, that's the Laplacian comparison. You have some beautiful rigidity result, like the Cheeger-Gromov splitting theorem. You can control the heat flow using the Liao inequalities. You can control the isoperimetry of your manifold using the theorem of inequality, and so on. So I could just go on and give results. So this is about smooth setting, and now let me smoothly move to the non-smooth setting. So, so what are the origins of the non-smooth setting of the non-smooth topic? So the origin go back to Gromov, who in the 80s introduced a notion of convergence for Riemannian manifolds. So usually we are always we always think of convergence inside a space. And the breakthrough of Gromov was to define a notion of convergence of the spaces themselves. Okay? So you can talk about convergence of Riemannian manifold, or more generally of metric spaces themselves. And they realized that if you have a sequence of Riemannian manifolds of a fixed dimension, n, which satisfy a lower bound on the Ricci curvature, say Ricci greater bigger than -1, then this sequence is pre-compact with respect to this Gromov-Hausdorff convergence. Okay? So it means that you will find a subsequence which converges to a possibly non-smooth limit space. And the limit space is a metric space. And from now on, I will call this metric spaces arising as limits of Riemannian manifold with lower bound on the Ricci. I will call them Ricci limits. Okay. And the natural question is, what can we say about the compactification of the space of Riemannian manifold with lower bound on the Ricci by, say, -1? And the hope is that this is interesting by itself, and then inspired by what we do in analysis, that we work also with non-smooth objects. These are also useful for getting new results, even for smooth objects. Okay, so we want to come back to smooth manifolds, and I will do that at the very end of the talk. So now we will do a journey. We will go together to the non-smooth setting, and then finally we are going to go back to the smooth setting, getting some new results there. Okay. So this program of Gromov was pushed in a very remarkable way by Cheeger and Colding, that wrote 3 fundamental papers about 25 years ago on JDG, where they studied, basically their goal was to study the fine structure of this limit space. So these limit spaces may be non-smooth. The easiest example that you can imagine is the case of a cone. Take a 2-dimensional cone, easy spin. This has a this contains a singularity, steeper, right? And then you can this cone can be approached by a sequence of smooth dimensional surface with positive curvature, and the curvature is going to plus infinity here, so, but it is still positive. Okay, this is the easiest example, and then you say, okay, but this is very easy because there's just one singular point. So singular is because the tangent space at every point. So at every point here, the tangent space is Rn, and the instant is not Rn. So it is. Okay, so can we get many more points? Yes. For instance, start from a tetrahedron. Okay. Now, by the same reason, so you can approach this tetrahedron from inside with smooth objects. Okay. And so now you get 4 singular points. Okay. is a bit better. Can we do more? Yes. So on each side, let's build a new tetrahedron. Now, one iteration. So on each side of the tetrahedron, you put a new tetrahedron, and then you double it. You have from 4 equal to 8. And then you keep going on any side. And then you're going to see that every vertex is going to be a singular point. And in the limit, you are going to have a space which has a dense set of singular points. Right? So this is still not the worst case. So just to tell you that you have some hope to do some regularity, but it's not the trivial issue. So you can have singular points, and basically the goal of Cheeger and Colding was what can we say on the structure? Is it we are surely singular point, but we have a regular set, how big it is? Okay. And I will skip this because it can get technical very quickly. Just tell me that there are very remarkable results. They can say that the singular set is small, so it has Hauser dimension 2 at least. And on the regular set, you have a nice structure. This was pushed by Colding-Naber more recently, and by Cheeger-Naber even more recently. If you have questions, I will be able to discuss it, but it gets technical very quickly. Just to say that there are breakthroughs in this area, and even if the limit space is non-smooth, it has some structure which is very remarkable. Okay. So, but what I want to stress instead is that this approach to Ricci curvature is kind of non-intrinsic in the sense that it is this approach is very, very powerful to study the structure of the limit spaces. It's very remarkable. But if you want to understand the more fundamental question, we'll say that is what is Ricci curvature for a non-smooth space? If I give you a metric space or a non-smooth space, and you don't know that it is limit of Riemannian manifold, can you say that it has non-negative Ricci in some sense? Okay? And I want to address this fundamental question in the talk. So then the first goal of the talk is to define in an intrinsic axiomatic way what does it mean for a non-smooth space to have Ricci curvature bounded below by some constant, and dimension bounded above, so Ricci bounded below by some constant, and dimension bounded above by some other constant. So lower bound k, upper bound d. And you can think of this class of spaces like weak or non-smooth Riemannian manifolds in the same way as in more classical geometric measure theory, we see set of finite perimeter or currents or varifolds as kind of non-smooth submanifolds. Okay. And why in classical geometric measure theory one introduces the finite perimeter or currents or varifolds is because they enjoy better compactness properties rather than the smooth objects, and are very useful then to prove even new theorems for smooth problems. And the long term is to do the same here. We already have some results. Okay, is the goal clear? Good. Okay, so let's start. So the preliminary observation is in which kind of object, in which kind of geometric structures can we hope to define the Ricci curvature, right? So we have seen very quickly before that sectional curvature is a property of length. So we can characterize sectional curvature via Toponov comparison just using the distance function. And this suggests that the right setting for studying sectional curvature lower bounds for non-smooth spaces is given by metric spaces. Okay, so which is a set with a distance. And indeed, one can take Toponov comparison as a definition of sectional curvature lower bound for a metric space, and that's indeed the approach of Alexandrov spaces. This is a beautiful field with very deep results by Burago, Gromov, Perelman, and it's a beautiful area. Okay, but what about Ricci curvature? So what we have seen before, very quickly, is that all the results, let me go back to the results. All the results about Ricci curvature involve both the volume and the distance. Take, for instance, the landmark one, which is Bishop-Gromov. Bishop-Gromov is a volume growth of metric balls. So you need a volume, you need a measure to say what's the volume of the metric ball, and you need a distance to say what's the metric ball. Okay? Second one, Lichnerowitz, spectral gap on the Laplacian. To define the Laplacian, you need both distance and the measure. Here is a bit more hidden, but it's because to define the gradient, you need the distance, and then to define the Laplacian, you integrate by parts. And so you need the measure to, so you need the measure to integrate by parts, and so on. All the others are on the same vein. Okay, so it turns out that if you see the theorems of Ricci curvature, they all involve an interplay between volume and distance. And so the natural setting is the one of a metric measure space, so which is a metric space endowed with the reference measure, okay, which plays the role of a volume measure. Okay. Now, in order to study Ricci curvature, we need a little bit of optimal transport. So let me do a crash course of I think just one slide on optimal transport. Just about notations. Okay. So from now on, XDM is a compact metric space. So XD is a compact metric space, and M is a finite non-negative Borel measure. If you're interested, actually, this can be generalized by saying that that XD is just complete and separable, and M is sigma finite. But for the talk, let's just stick to this case just to simplify the notation and to fix the ideas. So on top of this compact metric space, we consider the space of probability measures, which are non-negative Borel measures with total volume equal to 1. Okay, now there's a way using optimal transport to define a distance between two probability measures. Okay, let's see it together. Let's unroll this definition together. Okay, so basically the rough idea that the distance between mu1 and the mu2 is the minimal cost that I have to pay to transport mu1 into mu2. That's the rough idea. So how it is implemented mathematically. So what is a transport? A transport is by definition a probability measure, gamma, in x times x, such that the push forward on the first coordinate is mu1, and the push forward on the second coordinate is mu2. Okay, so this is you can think of gamma as a way of transporting the mass mu1 into the mass mu2. Now, what is the cost of this transport? We choose. You can make many choices of the cost. We choose as cost the integral of the distance squared integrated with respect to this gamma under the square root. And then we want to take define the distance as the minimal cost. So we take the infimum of all the cost among all the possible plots, all the possible way of transporting mu1 into mu2. Okay? It turns out is not too hard, but it's not trivial that this W2 defines a distance, and the metric space of probability measures endowed with this W distance is geodesic if and only if the underlying space is geodesic. So the idea is that you are lifting from the underlying metric space XD some properties to the space of probability measures. And the space of probability measures will, so studying the geometry of the space of probability measure with the W2 will tell you many good informations on the underlying metric space. That's the rough idea. Okay, so how to study the geometry of probability measures? Actually, it turns out it is very useful to consider functionals on the space of probability measures. So in order to keep notation simple, let me, from now on, assume a simplicity that all the probability measures are absolutely continuous with respect to the reference measure M. So M is given in the beginning, is a reference volume measure. If you are on a Riemannian manifold, you can think that M is the Riemannian volume measure. So for me, mu is always a multiple of M by a density rho. Okay, so it's going to be very useful to consider some functionals that take a probability measure and gives you a real number or plus infinity. And these are called entropies. And these are parameterized by a parameter n, which will take the role of a dimensional parameter. So for n equal to infinity is the famous Boltzmann entropy, which is the integral of the entropy of rho m is the integral of rho log rho, and this was introduced by Boltzmann in the context of statistical mechanics, and then rediscovered by Shannon in the context of information theory. And for finite n, instead, we have the Rényi entropy, which is minus n, the integral of the density rho to the power 1 minus 1 over n. And again, this was introduced by Reni in the context of information theory. So from contexts which are very, very far from geometry, which is very fascinating how things then intertwine. Okay, so you have these functionals, right? So the starting point of this theory is basically a characterization of the Ricci curvature lower bounds in terms of properties of these functionals. Okay, let me unwind this theorem, which is a collective effort of several bright mathematicians. It says that let's take a as Mathematical space a smooth Riemann manifold. Okay? So it means that I have a smooth manifold. As distance, I take the Riemann distance, and as measure, I take the Riemannian volume measure, all super classical. Then the Ricci curvature of this smooth manifold is non-negative, if and only if the Shannon-Boltzmann entropy functional is convex along geodesics in the vast space. What do I mean with the convex? What you expect? So given two probability measures, mu0 and mu1, there exists a geodesic joining the two, such that the entropy along this geodesic is convex. Okay, is a very simple statement. And let me just give a picture. So basically, here we have mu0, mu1. Here you're geodesic mu-t. Here you get the entropy. And what you say that the entropy along the geodesic. Okay. And let me give you, giving a proof is goes far beyond this talk, but just let me give you some heuristics why this statement can be true. Okay. And so here I'm picturing P of Japan. Let's go down to 10, which is the and here I'm drawing the supports of the measures. Okay. There is support of mu0. There is support of mu1. Okay. But what we know by classical optimal transport is that the optimal transport between mu0 and mu-t is performed along the geodesics of the analysis space. Right? So where is mu-t? So here is my mu-t, here is the entropy, and here it will be somewhere like that. Okay, so it will be intermediate points of the geodesics. Oh. We want to characterize positive curvature. Okay, so what we know from differential geometry about positive curvature? So we know that in positive curvature, think for instance on the round sphere, the geodesics tend to open up and then close. Okay, so tend to focus. So if you start open, then they will tend to come up together. So this will tell you that if you start from two measures, mu0 and mu1, which are quite concentrated, then in the middle, your mu-t will be more spread, and then it will be convertible. Now let's look at the entropy. What is the entropy? The entropy is this one. Okay. So you see that this entropy here is the Boltzmann-Shannon is superlinear. So it is higher if the measure is more concentrated. So the more concentrated is the measure, the higher is the entropy. So it is telling you that if at the endpoints you are more concentrated, the entropy is higher, and in the middle you are more spread, and the entropy is lower. So it's not exactly complexity, but it is suggesting that complexity could be something to okay? Some heuristics. Okay. And then the key remark is that while these statements, so the assumptions, while Ricci curvature non-negative is something differential, we need to take two derivatives of the metric, is something that needs smoothness. Instead, this characterization by saying that the entropy is convex makes sense for mathematical spaces. It is something that doesn't need any smoothness. And so this was the starting point of a very successful theory of Lott-Villani of measure spaces with lower bound on the Ricci. Basically, their idea is to take this right-hand side of the theorem, this characterization of Ricci lower bounds, as a definition of Ricci lower bound for a measure space. Okay, so you say that a measure space has non-negative Ricci curvature if the entropy is convex along geodesics in the Button space. Okay, so this is so if you now this is lower bound on the Ricci. Now, if you want to put an upper bound on the dimension, it turns out that it is more useful to consider convexity of the Riemannian entropy. So you say that your space is a CD 0 in space. 0 is lower bound on the Ricci and then n is upper bound on the dimension. If the n-dimensional Riemannian entropy is convex along geodesics in the Button space, and then you can also make sense of a lower bound on the Ricci by any constant k, serial constant, by considering more refined notion of convexity, which takes basically you are comparing with the model space. So for k positive, you're going to have some sign showing up. For k negative, you're going to have some symbolic sign showing up. But the idea is to compare with the model spaces. Okay, so this CDKN stands for curvature dimension condition. K is the lower bound on the Ricci curvature, and n is the upper bound on the dimension. Okay, so what to keep in mind for the rest of the talk? So this CDKN is a definition of Ricci curvature bounded below by k, and dimension bounded above by n in intrinsic mathematical way for measure spaces. So you don't need any smooth approximation. It is a definition which works well on the measure space itself. The rough idea is that the more convex is the entropy, the more the space is positively Ricci curved. Now, so far is only a definition, so some good properties. So first of all, it is consistent by the previous result that I was mentioning. So a smooth manifold satisfies the CDKN even only if the Ricci is bounded below by k and the dimension is bounded above by n. A key property is that, that this notion is stable under Gromov convergence. So if you have a sequence of CDKN spaces which converge in Gromov to a limit space, then the limit space is going to be CDKN as well. So if you remember the previous slide about Cheeger and Colding, they're interested in Ricci limits. So in particular, by the fact that this notion is consistent and stable, you get that all the Ricci limits are CDKN spaces because they are limits of manifold with lower boundaries. Okay, and then you have plenty of the properties. So basically, all the theorems of Riemann geometry with lower bound Ricci have been now generalized to the CDKN framework. For instance, let me just mention the Bishop-Gromov volume growth, but basically all the theorems you can imagine now have been done in setting. Okay, and then if you're interested in Fields structure, so what is a Fields structure? So a Riemann manifold is a smooth manifold, and at every point you have a scalar product. A Fields manifold is a smooth manifold, and at every point you have a norm. Okay? If you're interested in these objects, many people are interested in these objects, then there are good news because the CDKN structure allows for Fields manifolds. For instance, if you take Rn with any norm and with the Lebesgue measure is a CD 0n space for any norm. Okay? So it is very flexible. It allows for Fields structure, which is pro and cons. The advantage that you can allow this, so it is flexible enough to encode many structures of interest. The downside is that if you're interested in some specific properties of Riemann manifolds, like for instance the splitting theorem, they cannot hold here because they include things. So if you are interested in give a Riemannian, so let's give a Riemannian refinement of the possibly Fields-Larian CD condition. Okay, so how to discriminate between a scalar product and a norm? So the idea that a norm, that a scalar product is a norm which satisfies the parallelogram identity. So how to check the parallelogram identity on a metric space? The idea is to look at the differential energy, so integral of grad f squared, and if it satisfies the parallelogram identity, this should be something Riemannian. Otherwise, it should be something Fields-Larian. Okay, so defining this object, the differential energy, is something which is not completely trivial. You can do that. Why? Because basically, how you define it on a smooth Riemann manifold, you take the gradient and the L2 norm of the gradient. But what is the gradient is an element of the tangent space. And on a metric space, you don't have a tangent space, so you need to work. So what is helpful here is that it is not, you don't need the full gradient, you just need to know the modus of the gradient, okay? And this object is well defined on a metric space. It's called minimal Wigert gradient. So once you buy the notion of minimal Wigert gradient, you can define the Cheeger energy formally as the classical differential energy. If you don't buy it as a black box, let me just tell you in 2 words how to do it. So just take, you want to define the Cheeger energy of a function f, okay? Then take all the possible ways that you can approximate f via Lipschitz functions, okay? Now, if you have a Lipschitz function, then you know what's the modus of its gradient, is the local Lipschitz constant, right? Then take the L2 norm squared of the Lipschitz constant of the approximation, take the lim-inf over this approximation, and then take the inf of all the possible approximations in L2. This is by definition the Cheeger energy, okay? Anyway, think of it as a kind of metric counterpart of the differential energy. Now, the crucial observation is that if you take a Fizer manifold, M, the Cheeger energy is quadratic, in the sense that the parallelogram validity holds, even only if the manifold is Riemannian. So it's a good way to discriminate between Riemannian and Fizer. And so the idea of Ambrogi, Savaret, and Gigli is to reinforce the CD condition by asking that the Cheeger energy is quadratic. And this gives the RCD condition. Right? So the RCD condition is R stands for Riemannian, so it's the Riemannian CD condition. Is by definition, RCDKN is CDKN, or Lott-Villani, plus the fact that the Cheeger energy is quadratic. Okay, so you should think of this non-smooth space as a kind of non-smooth Riemannian manifold with lower bound on the Ricci and upper bound on the dimension. Okay? That's the definition. Now, some good properties of this class RCD. So the first good property is that it is stable under Gromov convergence. So in particular, the Ricci limits of Gromov Cheeger Colding are not just CD, but actually are RCD. Again. Then for the PD people, we know that the heat flow has very good contraction properties in Rn and with lower bound on the Ricci, and that's the same here in the node setting. And actually, one can characterize this RCDKN condition by studying the contractivity properties of the heat flow in the vast space. Then this RCDKN condition is equivalent to the Boxer inequality, which is very powerful in analysis. It implies the Liao inequalities on the heat flows. It implies you can generalize the splitting theorem of Cheeger-Moll to the non-smooth setting. Once you have the splitting theorem, you can start studying the local structure. Basically, what you can prove is that if you take this RCKN space is not smooth. It has some singularities. But how large is the set of the singularities? What we can prove is that take a random point in the sense that the set of random points is a set of full measure, then zoom, fix one of these random points and start zooming. What you see is Rn, okay? And this you see is like, so if you take a cone, if you zoom at the tip of the cone, you just keep seeing the cone. And on the other points, you see Rn. So this is a way to discriminate between the smooth, the regular and the singular space. Moreover, these spaces are rectifiable in the sense that you can have Lipschitz charts on Borel sets of full measures to Rn, and they have a constant dimension. Moreover, so this is local. So these are all analytic properties. This is structural property. And then you also have some good topological property. For instance, they admit a universal cover, which itself is RCD. So once you know that the universal cover is RCD, then you can start. Then you know that the volume growth in the universal cover correspond to a bound on the complexity of the fundamental group, and so you get also some topological results on this RCD. You have some good second order calculus, Hessian for W2 functions. You can check. There's a local Turova property which is far from trivial, which says that that is enough to check the RCD condition locally at near every point to get it globally. Which it is trivial for a smooth manifold, because because the Ricci bigger than k condition is something which is given pointwise as definition, while the RCD condition is global as a definition in the beginning. So having this local check is far from trivial. And then it implies sharp isoperimetric and Sobolev inequalities, like basically the one that you know in smooth spaces with lower bound on the Ricci, like the Bishop-Gromov inequality, for instance. Okay, so we have a definition, we have many good properties. Here I just mentioned a few. I could fill up the slides with good properties, but just to give you an idea of the good properties. Now, if you want to build up a good theory, you need to be sure that you are not writing theorems about the empty set. So you need to have a rich class of examples which fit your theory. Okay, you're not just writing theorems about the empty set. Okay, and we have already seen that Ricci limits are enter the class of RCD Kn spaces. Then I was mentioning before this class of metric spaces with lower bound on the sectional curvature. Now, in the smooth setting, it is clear that if you have, say, non-negative sectional curvature, then you also will have non-negative Ricci curvature, because the Ricci curvature is just sum of sectional curvature. And this is trivial in the smooth setting. It's far from trivial, but true in the non-smooth setting. So Alexander spaces of finite dimension are example of RCD spaces. If you can also put weights on the volume measure of a Riemannian manifold, you get a weighted manifold, and if then you can write down a tensor out of the weight, which is called Bach-Riemann Ricci tensor, and if it is, and this is bounded below if and only if the weighted space is RCD Kn. Then you can start doing some geometric construction, like taking cones over spaces. So, and if you take a cone of an RCD space, you still get an RCD space. You can also take quotients. You start from an RCD space, you take quotients under the group action of some group, and you still remain an RCD space. And then you can build other example using stratifications. Okay, so plenty of examples entering the theory and others. And now I would like to go back home. So we started from this journey. We went to the non-smooth setting. Now let's go back home let's get some smooth application out of it. Okay. So just to mention some application and connection to other fields. So there's some application to the Ricci flow. For instance, one can prove the isoperimetric inequality that was joint work with the Cavalletti. Can be linked very well with the Perelman pseudolocality theorem in the Ricci flow. And for instance, it was used recently by Liu and Sechelidi to prove new results in the Ricci flow, building on top of some RCD work. Then there's a recent proof of the Hamilton conjecture. So the Hamilton conjecture was a long-standing conjecture saying that take a three-dimensional manifold having Ricci curvature bounded below by positive constant times scalar curvature. So it's called Ricci pinched. Then the manifold is either flat or compact. It's a purely beautiful smooth statement. And there's a recent proof by these bright mathematicians, and the proof uses the RCD techniques in some. Basically, they have to take limits. The limits are non-smooth, and the limits are RCD spaces, and so it enters in the argument. Okay. Then there was a conjecture by Perelman and Petrunin in Alexander spaces. So these non-smooth spaces with lower bound on the sectional curvature. And I told you that these spaces are entering the framework of the RCD theory. And with Brouet and Semola, we prove this conjecture using techniques of RCD. And this conjecture basically tells you that if you take an Alexander space, then you always have an infinite geodesic, or more precisely, take a point and you shoot in almost every direction, then you will build a geodesic, which is infinite. That's trivial in the smooth case, but why is not trivial in the non-smooth case? Because if you take a cone, if a geodesic hit the tip of the cone, dies. Right? So basically, it is telling you that when you shoot a geodesic, it means that you can at least shoot one geodesic which never enter one of these bad singularities. And actually, we can prove that for almost every direction, it will never hit these bad singularities. It's built on top of previous work of Kapovic, Lichak, and Petroni. Then there is some connection with string theory. This is joint work with De Luca, De Ponti, which just joined here in Politecnico, and Tomasiello. So basically what we get is some bounds on the Kaluza-Klein spectrum of spin to field for spacetimes, which have some localized sources. So these localized sources should be thought as, point to us of higher codimension sources of the gravitational field. Since they are very localized, they create singularities in your spacetime, in your 10-dimensional spacetime of string theory. It turns out that these singularities entered the RCD framework, and then using RCD techniques, we could make some progress on some problems in string theory. There is some connection also to general relativity. Indeed, today I focused on the Riemannian signature of Riemannian manifold, but one can build up a predictive theory in Lorentzian signature. And in Lorentzian signature, you can characterize lower bound on the Ricci curvature, again, using optimal transport. And now you see that the Einstein equations are written in terms of the Ricci curvature. So we can give a optimal transport formulation of the Einstein equations, which holds in extremely low regularity. And then with that, we can extend some classical theorems of general relativity, like the Hawking singularity theorem, in Lorentzian spaces of extremely low regularity. So, for instance, the Hawking singularity was proved for smooth metrics, and we could say that this holds even if the space is highly non-smooth. Okay. And then there is application to isoperimetry, for instance, about existence of isoperimetric sets in non-compact manifolds. I think Pozzetto just joined also here, right? So you're making very good buys. So there is some very interesting work on non-compact manifold with negative Ricci, and some sharp convexity inequalities on the isoperimetric profile of manifold with lower bound on the Ricci. And again, by a group of bright young students, young researchers. Okay, so this was just to give an overview of application. There are plenty other applications to the smooth setting, but just a random selection of some of the applications that have been established. So let me wrap up with some conclusions. So in doing Riemannian geometry, one naturally encounters non-smooth spaces. Okay, so when, for instance, when you take limits of Riemannian manifolds, and taking limits of Riemannian manifold is a procedure which is used more and more often in modern geometric analysis, in contradiction arguments, blow-up arguments. When you have a geometric flow which creates singularities, like the Ricci flow, the limit often is non-smooth. Then also, when we take quotients of Riemannian manifolds, you can build up cones which are singular, or take suspensions or foliation. So singularities are kind of natural, enter naturally when you prove something even in smooth Riemannian manifolds, when you make the space move. Okay? So what is the message of this talk is that if you know that your starting space has lower bound on the Ricci, then the non-smooth object that arise using in this very natural operations still they are non-smooth, but they still have the negative. They still have a lower bound on the Ricci in this intrinsic wavy optimal channel. So they are RCD spaces. There are plenty of results of these RCD spaces, and so this class can be seen as a kind of a natural class of weak non-smooth Riemannian manifold with lower bound on the Ricci. This class has the big advantage of being closed under this natural geometric construction, like taking limits or taking cones, which instead force you to go out of the smooth triangle. And this is one of the reasons why I think they are useful. And yeah, I think it is the end. And thank you very much for your attention.
Okay, so thank you very much. So are there any questions or comments from the audience?
So thank you, Andrea, the beautiful overview. So 2 questions. You mentioned that you have almost everywhere local Euclidean structure for these spaces. You have convergence of blow-ups at every point.
So by definition, the blow-ups are the limits. So you mean uniqueness of the limit? You mean?
No, I mean, if you can prove that you have that you have a local conical structure at every point, like it is, for example, in the case of minimal surfaces.
Right. No. So there are counterexamples to this already for Ricci limits. So what you can show is that so you have 2 cases. So there's a dichotomy between collapsed and non-collapsed. So basically the non-collapsed is when what I'm saying is that this RCDK n is the upper bound on the dimension. If n is the dimension of your space, then you say that it is non-collapsed. In that case, Gromov inequality is very strong, and together with rigidity, the fact that you are equating the Gromov, even if you are a cone, you can show that all the blow-ups are cones. So the answer is yes in this case. So when n is the dimension, if instead n is just an upper bound and the actual dimension of your space is lower, then no, there are examples already of Ricci limits by Mengui, for instance, that you have tangent spaces which are not cones.
Okay.
And the uniqueness fades dramatically. This is also
Okay. And another thing is whether there is now maybe is in Riemannian manifolds you can talk about some manifolds and you can talk about the mean curvature of an immersion. I was wondering if there is an equivalent condition here.
So this is a program that we have been doing recently with Semola and with Cucinotta, student working with me, and we're interested in basically in minimal surfaces there. So we want to, and we start with codimension 1. So codimension 1 means that we can work with finite parameter sets. So there's a well-established theory of set of finite parameter in metric spaces, mainly due to Ambrosio. And with that, you can say that a set is locally parameter minimizing. And then you can study a little bit of, we started to study the structure of a set which minimize the perimeter. And you can say that the set is a local perimeter minimizer, and we can say that is a minimal surface by studying the Laplacian of the distance function. But this, for the moment, is codimension 1. For higher codimension, probably it will be useful to work with the theory of currents by Ambrosio Kirchheim, but for the moment, we start from codimension 1, and then in the future, we see if we can go.
Thanks.
Thanks for the question.
Okay, other questions? Yes.
In Riemannian geometry, Dirac operator plays a role.
Sure.
Are there notions of Dirac operators on these RCD spaces? The first question. The second is if what happens to the limit of Ricci bounded below spaces in the limit when the Cheeger energy is no more a Dirichlet form, is no more a quadratic.
Right. So right. Let me start from the second one. So this was already understood by Cheeger and Colding. So basically, let's start from smooth Riemannian manifold. So you have a sequence of Riemannian manifolds with lower bound on the Ricci. The Cheeger energy is quadratic because they are Riemannian manifold. And it was already understood by Cheeger and Colding that if basically they prove a spectral convergence of the Laplacian, they understood that the limit is going to be a Ricci mid space is a metric space. They proved that you have a good distance, good measure, and that you have a well-defined Laplacian, and the Laplacian is still linear in the limit. And if the Laplacian is, and you can show that the Laplacian is linear if and only if the Cheeger energy is quadratic. So basically, it's already understood by Cheeger and Colding that thinner manifold never arise as limits of smooth manifold below boundary Ricci. So you don't lose the quadraticity of the Cheeger energy when you pass the limit. So this RCD is closed under convergence. Regarding the first question, so I think this answered the second question. And regarding the first question is interesting. For the moment, is not done, the Dirac operator. I don't know much about the topic. As far as I remember, usually the Dirac operator is defined for spin manifold, right? You need a spin structure, which is which at the moment we do not have a notion of spin structure on a metric space. So basically, say the problem is almost at a fundamental level. So on differential geometry, you have vector bundles because at every point you have a tangent space which changes smoothly. And then if you don't want the tangent space, you can put a more general bundle, then you can study section of this bundle and differential operator on these sections. When you're on a metric space, you do not have this tangent space. In RC spaces, you have it almost everywhere, which is already something. But you have no way of saying that a section is smooth or the best you can say that a section is Borel measurable. So I think it's a very nice question. The answer is that maybe in the future we could have some spin structure defined almost everywhere on an RC space, and maybe with that one can build up a Dirac operator, but for the moment it's very speculative.
Okay, so thank you very much. I have just other questions, sorry. I have just a curiosity. So you mentioned very relevant applications to the smooth setting of this theory in the smooth setting, in the Riemannian case. So, but you didn't mention any application in the Lorentzian case of the theory that is in development about this normal setting. So are there,
for instance,
are there any?
Thanks for giving me the opportunity to advertise the recent work with Fabio. So we could prove, so using this optimal transport approach, we could prove a seemingly new isoperimetric inequality in the Lorentzian setting, which let's just give it a picture. So it's the following. So take a Lorentzian manifold. So, G with say that the Ricci curvature is non-negative in the Tanner directions, which means that the Lorentzian manifold, you always have a cone. So at every tangent space, you have a cone, which is the one where G is equal to 0, and in interior G is negative. GDV is negative, and the vectors inside are Tanner. Okay? So you ask this condition on the Tanner vectors. This is called strong energy condition, and it's one of the assumptions in the singularity theorem, for instance, of Hawking. So it's an assumption which is related to energy conditions in activity. Okay, then take two surfaces. Take for instance two Cauchy surfaces, sigma 1 and sigma 2, with sigma 2. So if you have space-time, you have a direction which is time, right? So you want that sigma 2 is in the future of sigma 1, and you write like this. So sigma 2 is in the future of sigma 1. And so consider this region here. Okay. And let's call it omega. Okay. So what we prove is that if you take the volume of sigma 2, this is always less or equal than the area, then the volume. So this is the n-1 dimensional volume. Is always less or equal than the n-dimensional volume of omega divided by the time that lapses from sigma 1 to sigma 2. Time from sigma 1 to and everything is divided by A. Okay, so is an area bound on Cauchy surfaces in terms of the volume which is enclosed. And this seems to be, so I stated it for smooth manifold. Actually, we prove it in the non-smooth setting with optimal transport tools. And it seems to be a new kind of isoperimetric type inequality in Lorentzian spaces. And if you, I don't want to talk 30 minutes on different, just that if you choose as your space-time some classical solution like Schwarzschild black hole, it will give you some new information, some similar new information on black holes. So there seem to be some.
Okay. Okay. So thank you very much. So let's thank the speaker again.